Okay, I feel like I've got a lot of digging out to do. And having people come to my office hours today was pleasant because that helps me understand where you're at. I mean, I haven't read the surveys yet, and that would help me more probably because I asked you to comment on that. But we'll proceed down through the linear flow of the book, and then what I want to do, or the notes I wrote, and then what I want to do is come back and start looking at some of these problems that are in the homework assignment, mostly looking at the solutions, but hopefully you'll be interactive and ask me questions. Because the problem with teaching this class, and it happens every time, Dr. Price, who left us a year and a half ago, taught the class when she came, and I had taught it before then. Dr. Zemer, one of the authors of the book, used to teach it until he retired. I think I told you that the 7th edition of the book is in preparation right now, though, so he's still actively involved with writing. He's just not teaching anymore. But one of the things that always happens is how do we get started and how do we bring the linear systems theory background that you've had, kind of make it coalesce into something that we can march forward with to do the communications theory. It's kind of a hodgepodge because we have everybody that's come from a different set of teachers even. We've got juniors and seniors and graduate students in here. And how many different people I've been teaching 2610 now even. I haven't taught it for a while, but most of you probably had Mark Robinson, Les Teekamp, and Professor Harrison just started this fall. I guess a couple of you had me, but everything is done a little bit differently. And then 2205, Dr. Wong always does that. Dr. Price used to do 3205. And then Dr. Trimboli's been doing it. So his contribution is the most important. How many of you had Dr. Trimboli for 3205? I'm guessing he's pretty consistent in how he does that. That's where you got your Fourier officially, right? So let's just continue on from last time is what I'd like to do, and then we'll, like I said, circle back. So last time we had reviewed through some line spectra ideas. Now we're going to jump and look at singularity functions. Not spend a whole lot of time. I'm going to skip over some of the extraneous stuff to keep moving quickly, but definitely need to use a delta function. So the delta function and the unit step are the two primary singularity functions. And a lot of things are fresh in my mind from editing the sections in my book at the beginning of December in this area and what my editors were saying. And one of the dummies type questions they asked me, why are they called singularity functions? So I can ask you guys that. Why are they called singularity functions?
They happen at a single instant in time.
Okay.
Some event occurs in a single instant time.
Like the step function. Yeah. The step, for example, is not defined at t is equal to 0. And the impulse is extremely mysterious. A function that has unit area, takes up 0 width, seems like it should have infinite height, right? But yet we draw a picture of it with the height representing what its area is. All of that stuff, doesn't that swirl around and add confusion? Or not? I mean, I'm not confused anymore, but I try to remember what was it like in the beginning. So that's why the unit impulse function is defined in this operator notation, or operational properties idea. Its area is 1, and it has the property that it's 0 everywhere except where it turns on, which is when its argument is equal to 0. You can put it inside an integral next to a function, and it will sift out the value of that function. And then there's more properties on the next page. But you know, this sifting property is probably one of the big uses of it. And then just simply to represent things at a point, we use the delta function all by itself. So the sifting property, though, when you look at how the delta function operates, if you have a waveform, if that's the x of t, and the delta function was sitting, not very straight, but sitting right in there at t naught, it's able to come along because it actually has that unit area. You can think of it as being maybe a Gaussian pulse shape or a rectangular pulse shape. it applies that area as unity, and it multiplies times the function, and then as you take the limit, as the delta function shrinks up to become the idealized delta function, it ends up pulling off this functional value right there, x at t naught. And if you think about it that way with some pictures, it definitely is not too magical anymore. But it still is an idealization at that. I'm going to say more about that in a little bit further down here. Some properties. This property is, I don't know, I just call this more exotic. It's more of an exotic property, if I spelled that right. Exactly a popular, is that right?
The C should be.
Yeah. Let me just say I said it and I won't have to write it. It's if you're rescaling the time axis, and we don't do that very often. But this one, it's definitely, all the models we use for a delta function are even. And the sifting property, like we already went through, is very handy. And you also notice that these things are strict inequalities. And the reason for that is if the delta function was sitting right here at 0, let's say, and you were integrating something over this, well, if the delta function was right at the end of the interval that you were integrating over, say from 0 up to 1, and you're trying to use the sifting property on that, you kind of have a little bit of a problem. What you could do, if you really wanted to be fancy, though, you could say that we got half the delta function inside of there, and we get half that x at 0 out of there. But this definition just says, let's not go that far. Let's not be that precise. It's got to be interior to the interval, is what it's saying, for that to work. And then the sampling property kind of follows from that. It says that if this is really what we're going to do with the delta function times a continuous function, it's like saying we're just got a delta function whose area now is x at t0. Derivative property is kind of exotic as well. So I'm not really going to go into that, but I just might mention now that the first derivative, did that get talked about anywhere, what the first derivative of the delta function is called? No, that's the integral. That's the one we definitely care about. But the first derivative is, like I said, kind of exotic. It's called a doublet. It's because it's like if you whack something, you get a derivative, and if you take the derivative of whacking something, you'd get a quick spike up and then a spike back down again, and that's called the doublet. It has to do with the test function model, which I can show over here in a second. We actually we'll be using that in a Fourier transform example too, so it's maybe important to say a little bit about that. A test function for the delta function is a rectangular pulse, and this is something that I'm not sure if it's burned into everybody's brain, but it needs to be burned into your brain for this course. That it was earlier, I think, in the first page. Pi of t over tau is the pulse that has height 1 and runs from minus tau over 2 to plus tau over 2. And then by changing tau, you can change the width of the pulse. And you remember that the base of that rectangular pulse is always whatever that argument is. That controls the width of the pulse. So the full width of the pulse is tau, but if it's centered on 0, like it is right now, it's going to go from minus tau over 2 to plus tau over 2. Everybody got that loaded back in your brain? This is almost universal in almost all books too, but it's not 100%. Some books use a different symbol. So it's a rectangular pulse, and then this kind of mates up with the other one that I talked about last time, the triangle. Just thought I'd review that since I'm running on this right now. The triangle is a little bit different, and this is something that you just got to commit to your memory. The triangle has this parameter tau to control its width, but its full base width is twice that parameter, so it goes from minus tau to plus tau. Now, how do you remember that? This came up in my book too, where I tried to put in some memory aid. But you have to remember convolution for this memory aid to work. Does anybody remember what happens when you convolve a rectangle with itself? You get a triangle, right? And the triangle is twice the width. I mean, we're going to review through that a little bit later when you look at convolution, but a convolution always starts at the sum of the two starting points of the two waveforms involved and ends at the sum of the two ending points. So if you convolve a rectangle with itself, the starting point would be at, minus tau plus 2, tau over 2 plus minus tau over 2, which would be minus tau, and it would end at plus tau. But I'll go through that again. That's the thing about linear systems. There's so much little detail stuff, but there's ways of remembering it. All of us are human, and our brains are fragile, so we come up with ways of remembering things. Silly ways, maybe. It's whatever works for you, though. That's what it is. So the triangle could also be used as a model for a delta function, right? Because it satisfies the symmetry properties. All you'd have to do is scale the amplitude, and you could have it work. But the sinc squared function is another function that works. That's this alternate one down below here. We haven't gotten to the sinc function review just yet, but rectangle is good. So here's a couple of examples of rectangles. And if that approximates a delta function, then we can talk about how the doublet would come into being, because if I didn't differentiate a step function, which I guess I should look at first, and I'll come back. The step function is right here. It's a function that is 1 for t greater than 0 and 0 for t less than 0. And that comes about by integrating through the delta function sitting at 0. And then you can turn this around and have that the derivative of the step function must then give you the delta function. And this is what I call operational math, which I had to come up with a different name for this because the editors did not like that. I don't remember what I ended up calling it, though. I call it operational math because you can't really take the derivative of a function at a point of discontinuity, can you? But what can you do if you wanted to take the derivative at a point of discontinuity? How could you fake it? You could take limits, right? You could find out what's going on to the left of the point of discontinuity and what's going on to the right. But right at the point of discontinuity, if we have a discontinuity, we just have to agree what we're going to do in this operational math idea, and we say that that's where the delta function comes in. Question?
Yeah, can you go back up real quick to the rectangular pulse?
Yeah, I wanted to go back to it. Now I can, maybe. What's the question?
Okay. Well, it was just something in the definition that I thought looked wrong. So that's why I was...
Now, the area of those rectangles has to be 1, right?
Mm-hmm.
So...
I'm not talking about right here. But
oh, further up?
yeah.
Okay. Over here?
Right there for the...
right for the other lines.
The pulse one.
Yeah, the green one?
Well, the actual formula or definition of the pulse.
Okay.
It says that
The capital pi.
absolute value of t is less than or equal to epsilon. Should that be 2 epsilon? Because it's the same as the denominator of the...
No.
No?
Because remember, for the rectangle pulse, it runs from half the pulse width on the negative axis to half the pulse width on the positive axis. So that's why it's got to be epsilon. If the full width is 2 epsilon,
Yeah,
there's an epsilon on this side and there's an epsilon on the other side.
Oh, okay, I see.
Does that make sense?
Yeah.
Okay, now I can go back over to here, since we're just talking about the operational idea of taking the derivative of a function at a point of discontinuity is that when we have a step function involved, we just declare that that derivative will equal the delta function. That's sort of by agreement. And we can approximate that with the pictures up above, which is what I'm going to go look at. If you were to go into a calculus class and talk to a math professor, they would be rather stressed about that whole thing, because it's something that's not quite natural. But engineers do this because we want to have these operational or type properties that make sense to us. On paper, we want to keep the math simpler, and that's how we do it. Really, we're approximating reality. We're idealizing reality, is what I should say. There's no such thing as a true mathematical step function like it's defined here. It just doesn't exist, because physics doesn't allow for things like that to happen. You cannot make the voltage across a resistor, or anything for that matter, to instantaneously jump. There's going to be some distributed, resistance, capacitance, and inductance, which is going to keep it from making those instantaneous changes. So a simplified model of a step, or a more realistic model for a step function is probably something like you would imagine measuring on the oscilloscope in the lab. It would be something that would come along and it would transition like something like that. This is even pretty idealized. And it would be going through approximately 1/2 right at 0. But that's even pretty idealized. That straight line piecewise approximation. If you were to do this in the lab with a square wave generator and zoom in on the rising edge of the square wave, you're actually going to see some rounded edges on there, right? And most good pulse generators have a knob that you can use to control the rise and the fall time. You can actually slow the edge down if you want to. So that's the reason why I call it operational math, I guess, because in reality we don't really get into trouble with anything we build because it's all physical. But the math on the page is just trying to simplify it into a nice compact mathematical representation, and we just work with that operationally, and we don't violate anything in physics. So what goes on here with the rectangle then is its area is always equal to 1 when we're using it to approximate the delta function. And then if we came along and wanted to take derivatives of this approximation to go after the doublet like I was talking about, what would happen if I tried to go after the doublet, just as a quick little example? We'll take the tall rectangle. Using this operational math idea, we take the derivative, and what would happen? As we step up at this point, we're going to get a positive delta function, right? So it's going to come up like that with a spike, and then it goes across. There's no derivative. The derivative is 0 there, and then when it jumps down, it's going to get a spike downward like that. And then as the limit as epsilon goes to 0, the two spikes come together, and that's the official doublet, where it jumps up and jumps down. I think actually that occurs in an elastic collision, or inelastic. What am I thinking of? When a cue ball strikes a pool ball or anything. Think of physics when you have collisions and you have momentum transfer. Yeah, perfect. Whatever the one that doesn't lose any energy. Is that elastic or inelastic? I've lost track of it. Okay. I'm not positive though, but there's analogies to mechanical systems and electrical both with those types of behaviors. Don't worry about it. It's just something for your bag of trivia to say you know what a doublet looks like. It's 2 spikes on it. And we'd get that by taking the limit now if we wanted to. But really we're good enough for this whole semester by just knowing the relationship between the step and the delta function. But of course we have to be able to move that around on the time axis too. So I'll skip this example. This actually takes you through the doublet idea, I think, is exactly what this was doing, if I'm thinking right. Yeah, it is. This is the doublet idea right there. Okay, so now moving along to a different topic for the time being. signal classifications. For the purposes of this class, there's two types of signals that we'll be dealing with that are of interest. We'll be dealing with periodic power signals and aperiodic energy signals. So a periodic power signal is something that runs continuously over all time. An example of that is a sinusoid, a pulse train, a square wave, triangle wave, any of those things that just go on and on and on. Energy signals are things that are there for a brief period of time and then gone, like a single isolated pulse or a sequence of pulses. It might be a comm message that puts up a burst of pulses and then is gone. That could be or a radar type signal with low duty cycle might better be viewed as an energy signal as opposed to a power signal. So from circuits, the power, instantaneous power, is the voltage times the current, or it's I squared R, or it's V squared over R. Any one of those models works for instantaneous power. What signals and systems people do is we abstract things to go on a per ohm basis, and we would effectively, what the per ohm basis ends up meaning is, think that R is equal to 1 ohm. Just for convenience, so we don't have to worry about carrying around R when we're doing modeling. Now if you wanted to do modeling with the impedance in there, or the R value, then you just have to add it back in. And those of you taking the Comm Lab, that's exactly what you have to do when you're taking measurements with a spectrum analyzer. You have to remember that R is actually there and it's 50 ohms. But systems engineers are lazy just like anybody else is. They want to simplify their work, and if we can just drop R out, then we can just say we square the current or square the voltage, and in either case we have watts. And we just think of the ohms as being a 1 ohm resistance. It's a good quiz or exam kind of question to say, suppose I add the resistor back in, what is the true power? So you just have to either take V squared over R or I squared times R, and then you'd be able to convert any quantity to actual power in a particular impedance environment. Okay, the energy is related to the instantaneous power by integrating it over all time. So I squared, or this could equally well be V squared. In our 1 ohm impedance system, it doesn't really matter. It will give us units of joules because we're taking and doing what? I mean, this is where I have to stop and think to myself every time, but this is a good engineering trait to have. Whenever you deal with units, what's something that you've been taught to do when you have units involved in something? Don't you want to see things balance out and make sense? If you've got units going on somewhere, just check it to make sure. So we know that I squared or V squared in a 1 ohm impedance system would be watts, but then we have a dt in there from the integral, so that's going to be watt seconds. And isn't that joules? Correct? Okay. And then the next line that says power, that's taking the energy over all time and normalizing it by the time and taking that limit, and that then divides by time again, so that takes you to watts. And this is where I made some observations last time, and then I'm going to say some more. Energy ends up being easily calculated in this form. Just integrate from minus to plus infinity for finding the energy, but finding the power, you have to take the limit, because you just can't integrate from minus to plus infinity and cope with that being infinity all at the same time. You have to do it in stages. But the good news is, if you have a periodic signal, there's, I think, a little proof in the book that says if a signal is periodic, all you need to do is integrate the quantity magnitude squared over one period and then divide by that period. is this sticking out from previous class pretty strongly, I hope? I think this is also called finding the RMS power in a signal, if that means anything. I've never taught circuits my entire life. I've taught signals and systems and a lot of other classes, but I haven't taught circuits. I think in circuits they used to call it, we used to have a unit on RMS voltage, which is just relating that to the RMS power by taking the square root. But so this is called average power, total energy and average power. And then we have the classifications I was talking about. What classifies a signal as energy is if the energy is finite, so energy has to be finite, and of necessity then if the energy is finite, as you take the limit, the power is going to go to 0. On the other hand, if the energy is infinite and the average power is finite, then you have a power signal. But there's actually a third class. If both of them go to infinity, then you have neither a power signal nor an energy signal. That's a mathematical curiosity, I guess, only because if a signal can produce infinite power, what would we have? Yeah, and I think we would have solved the energy problems that we have right now, right? If we had the capability to have some source of infinite power. So don't worry, I don't think it's going to happen anytime soon. But energy and power is definitely the two categories that you have to be aware of, though. So this real exponential provides a good example of a signal that can take on all three of those forms just by choosing the exponent alpha. So usually you think of an exponential as something that comes along and spikes up and then decays down. So a e to the alpha t u of t would just do something like that. But that's only if alpha is positive. So that's the energy signal case. And that would be called an aperiodic signal because it just has one event. It doesn't repeat itself. It doesn't contain an infinite amount of energy, so it's called an energy signal. Just that one event has this amount of energy in it. If, on the other hand, I set alpha equal to 0, then I've just effectively got the step function in the signal. And that obviously has infinite area, and if you square it, you have a squared, and you're integrating from 0 to infinity, and that goes to infinity. If you try to calculate the average power, though, in that signal, you can do that as I've done down here. I've taken a limit, and then I've set alpha equal to 0, and I get a squared over 2. And I set up the limit and did the integration and then let alpha equal to 0 and so on. But could you start here and get that answer just the same? I'm just curious if you're able to see that. If you had a battery that was always charged to A volts from the beginning of time to the end of time, what would the average power produced by that battery be? The average power is just instantaneous power divided by t, so I guess I'm thinking of intuition now. It's just v squared times t over t as the limit as t goes to infinity or minus to plus infinity. I guess what I'm going after is just simply saying it's a squared. That's the power it's going to produce for all time. Average power, I mean, it will produce. It'd be a squared. Pardon me? So if it's only available for half the time, namely from 0 off to infinity, which is what the step function does, that's how you get the a squared over 2, because it's divided by 2, because it's only on half of its lifetime. Average power is like in problem stats, it's an average, because the word is average power, so it's averaging over all time. Produced no power up until t is equal to 0. It produced an instantaneous power of a squared watts for t greater than 0, but on average over all time it's half of that. That makes sense if you think about it that way. And if alpha is less than 0, then you've just got this unboundedness where it just exponentially grows. And that's not power or energy. I don't even know if the sun is capable of that. I mean, I can't remember some of that analysis from physics, but okay, I was going to do something with that, but I think I'm just going to go on to this next couple of examples and see where that takes us time-wise. Okay, now that we've looked at these, gone through again these signal classifications of energy and power, this is just going through the calculation of the average power of a cosine. It's not a real stunning analysis because you've seen it before. As a matter of fact, my guess is if you just saw that that is a cosine wave and I asked you what the power is in that signal in a 1 ohm impedance level, don't you just snap your fingers and say, I remember, for the sinusoid case, or not? Does anybody remember? This is part of the COM lab this week probably too, to just have it right on your fingertips. A squared over 2. Does that amplitude squared over 2? Does that ring any bells for a sinusoid, the average power? Because remember, the RMS value of a sinusoid is what? 1 over the square root of 2, right? So it's that 0.707 stuff that you probably remember. I'm asking these little questions because I'm just trying to find out where your brains are at from things you learned before. And I'm getting a kind of a lukewarm feeling right now on that one. I mean, I just got to know, so. It's not totally cold. It's just not really warm, that's all. So just to prove through that, though, I took the definition here and I checked the energy of the sinusoid, and yeah, that goes off to infinity. Does anybody have a problem with that? You square a sinusoid, you square or take the magnitude squared of any signal, and it's always going to be positive, right? And if it's periodic, so it runs on forever, what happens when you integrate something that's always positive? You get infinity, right? So whether it's a square wave or a triangle wave or a cosine wave, and this just validates that just by integrating and using the integral of a cosine function, or cosine function squared. As a matter of fact, just by way of review, whenever do a cosine squared, you have to think 1/2 plus 1/2 the cosine of twice the angle, right? So that's what I did here. This is the 1/2 that comes out of the squaring. Remember, cosine squared of theta is 1/2 plus 1/2 cosine 2 theta. Since I'm mentioning that, what you need to do, I have little post-its in my book, what you need to do is go back to the appendix in the book just so that you can always pull these out. On page 721 is where the trig identities are. I mean, I practice at it a lot, so I remember it, but you might want to just put a little post-it sticker right there so you can always flip to that when you're trying to remember stuff. Euler's identities are there. Some more intense trig identity things that we don't need are there as well. Because again, I don't know where your memories are at on this stuff. So because I did that expansion, that's the constant term, and the 2 is sitting over here, and then this is the double angle part. And when I integrate that as n goes to infinity and I integrate over multiple periods, what's that piece going to go to? If I'm integrating a cosine, that goes to 0, right?
Yeah.
Because I've got a signal that's just going along like that, and that integrates out to 0. And that's really the origin of the 1/2 in the a squared over 2 formula. There's where it comes from, is right there. It's from that trig identity. Because the second term goes away, the first term survives, brings in the 1/2, and the a squared is sitting there. And then you have t naught from integrating a constant over one period, and that gives you the infinity. But when you then come in to do the average power, you get to divide by the time that you're averaging over the nt naught, so that nt naught works up against the n and t naught, and those guys cancel out, and that's how you're left with the a squared over 2.
Okay.
Is that right? Is that right? Again, I don't know. Remember where you last saw that? Was that 3205 or further back? Okay. In this class, it's just taken for granted. It's a squared over 2. I mean, just remember it. We'll look at some other signals that aren't, a squared over 2 is particular to the sinusoid. It doesn't work for other waveform types. Okay, now we want to go look at Fourier series, and I said I would skip over the generalized Fourier series, which is like a expansion that you'd see in a linear algebra class. It's pretty cool stuff, but I just can never find that I have the time to really delve into it. So what I want to do is just go right into the Fourier series. And the Fourier series that's needed for this class is complex exponential type of Fourier series. So because I'm skipping the section on the basis functions and everything, this expression right here doesn't make a whole lot of sense, but what's coming up over here in the blue box is the core of the starting point. It's just saying that you can represent a periodic signal of period t naught using this expansion, where you've got coefficients x of n times complex sinusoids to represent a periodic signal. And the equation for finding the coefficients is this integral right here that takes the waveform, multiplies times the complex exponential with a negative exponent and an arbitrary harmonic number n, and gets the coefficient. I'm going to come back to that equation in a second, but I just want to alleviate a little bit of stress and strain about Fourier series, because I know that if Fourier transforms don't bug you a lot, Fourier series bug you even more. It's just kind of what I've learned from teaching, and I had reinforced by my editors recently that, I'm finishing editing a chapter right now on Laplace transform. Almost no complaints, almost no issues from anybody, and I'm thinking to myself, why is that? I think it's because it's just so much easier to follow, whereas in the Fourier chapters I was just eaten alive by comments and things they got to fix. I think it's universal, so if you can take comfort in that. You're not better than anybody else, but you're not worse than anybody else either, so just be at ease with that thought. But one of the neat things about Fourier series is that they are unique, meaning that if you can find the Fourier series representation by another angle of attack rather than having to use this thing called the Fourier integral, or Fourier analysis equation, I guess is the right way of saying it, you're home free. So take cosine squared omega naught. You can expand that out from the trig identity, which is what I did here. And then you can take Euler's identity and break the cosine of 2 omega naught up into a plus exponential and a minus exponential. So this right here that's your That's the Fourier series just by inspection, because you broke it down into the smallest pieces you could using trig and then Euler's identity. All I have to do is just look, compare this up to here, and they sort of should pop off the page at you. You can see omega naught is there. All I have present in this waveform is the fundamental. All I have present in the waveform is a constant, which is the DC term. So that one must be x0. And what are the other two that are present in this case? So the 2 omega naught term has got to be the second harmonic, right? It's at twice the fundamental. So this must be x2. And then this one, x of minus 2, right? Now there's something you could do here. I'm not going to try to scare you a whole lot, but because of the fact that I don't see the fundamental represented in this expansion, I could re-index everything, and I could say that the fundamental of this signal is actually not at omega naught, it's actually at 2 omega naught. I could just arbitrarily say that because I don't see the presence of the fundamental. But I don't have to do that. That's kind of confusing, but the math would allow for that. The reason why I might not do that, though, is suppose I had a circuit like this, or a system. Suppose actually I had, I'll just call it V of t went in, and this was x of t that came out. So suppose I was feeding in over here a cosine at omega naught t, and what would come out of my system would be cosine squared, and in that case I'd probably want to keep the notion that the fundamental is omega naught, and then what comes out of the system after it gets squared is a constant plus the second harmonic. In RF systems, this might be called a frequency doubler, because I've created a double frequency term, and then what would I do about that 1/2? How could I get rid of that? If I want to get rid of the constant term, how could I get rid of that in electronic circuits? Yeah, a coupling capacitor would do that, right? Just have it AC coupled so I don't pass any DC. Or have a transformer. You might have a transformer in there. You might do this with an RF transformer and then have some diodes that are doing the squaring operation for you. I'm just trying to give you some physical representation. So here's the summary of the coefficients. Okay, another idea is that the book introduces, just for ease in doing things later on from some of the other parts we're going to get to, is introducing an operator called the time average operator. And the time average operator is just an integral that can average over some interval that is defined to be the entire time axis in this case. So the time average operator just takes the signal and averages over all time. It's a linear operator, so that if you take the time average of a linear combination of two signals, you get that same linear combination of the individual time averages. If a signal is periodic, it says that the time average operator only has to average over one period. The way I could think about that is, suppose this is your time axis in here, and I've got some waveform that's playing out in here. And this is one period sitting in here. This is another T0 period. Why should I bother to average over all those multiple periods? I can just average over one period and call it done, because the integral over all those adjacent periods is going to produce the same answer. So that's kind of where this idea comes from. Well, the idea of the time average operator then can be used to represent the Fourier analysis, if you want to, by just saying I'm going to time average this quantity, x of t times the e to the minus j n omega naught t, and that will give me my Fourier coefficient. And actually, this is kind of set up to the generalized Fourier series idea, and I'll just throw this out there and see what you think of it. This actually tells you how the Fourier analysis equation, which gets you the x of n, works. Everyone in here has had linear algebra, I think, haven't you? Taken that as your math elective, probably. Do you remember something called the inner product or the dot product? Remember the dot product, right? The dot product gives you the projection of some quantity of interest, say the vector A, onto some coordinate in the system. Like A dotted with the I unit vector gives us the component of A in the direction of the I unit vector. Remember that from physics? Well, the abstracted version of the dot product is you can define an inner product in terms of functions. And I think you do a little bit of that in linear algebra. Does anybody remember abstract vector spaces, where you can have the notion that an inner product can be generalized to functions rather than just things like vectors in space? I'm just sort of teasing your brain a little bit with this. I'm looking up in the corner because when I took statics and dynamics, the professor would always point to the corner and say, there's your I, J, and K unit vectors. They're sitting up there in the corner. Did you ever do that in physics?
Yeah.
That's very concrete. Maybe that's why people like mechanical engineering more than electrical, because there's so much concreteness in stuff that they do. But the abstracted idea is pretty powerful, and if this can actually be viewed as a dot product. So we could think of there being a dot in here, and the time average operator would be the inner product operator. And what we're doing with the Fourier analysis equation to get the coefficients is we're dotting our signal x of t against this other function, the complex sinusoid. And what the coefficient does then, it tells us the strength, or the amplitude, magnitude and phase actually, of that signal x of t lying along that complex sinusoid.
Real and imaginary.
It has real imaginary parts, but it's telling us how much, what's the complex amplitude associated with x of t lying at that frequency, n omega naught.
And does that assume that x of t is real, or can x of t be complex?
It can be complex too. For this class, it's real, so don't get worried, but it could be complex too. It's pretty powerful stuff, actually. And that's why the Fourier coefficient pops up as either being 0 or some number. Like in the cosine squared, there was no fundamental, right? So when the inner product took place here, x got dotted with that function e to the minus j omega naught t. It turned up a 0 because there was no energy at that frequency that comes out from the Fourier coefficient. It's interesting, right? I wish I could be, I can smile about it, because once this stuff starts to really turn on in your brain, it's like, hold on, because you got all this knowledge now and you can apply it to thinking about things. Now you can't solve the problems of the world, but you can solve a few problems that you have right in front of you, and that's kind of where it's at. So it's pretty cool. Okay, there's some nice symmetry properties of Fourier coefficients that were already demonstrated. Namely, that they're conjugate symmetric is the main property here. As long as x of t is real, which is all we really care about here, they're conjugate symmetric. So x, in particular, that says x of minus 2, like the example we looked at, is equal to the conjugate of x of 2. And if a quantity is equal to, if one quantity is the conjugate of the other, that means the magnitudes are equal and the angles are opposite, right? So if I was to dial back to this little expansion, this simplified expansion over here, that's how come at plus and minus 2 we were getting 1/4, because it's 1/4 and the conjugate of 1/4 is still 1/4. So that's the symmetry property. There's a proof of it right here. There's also some very powerful waveform symmetry properties that we come along with. There's 3 of them listed here. And these are useful for those of you taking the CommLab, actually. And this is probably that's the one that actually is the most important one, I think. 1 and 2 are nice. If you have an even or odd signal, you can say that the coefficients are purely real or purely imaginary. And that's okay on paper, but when you're in the lab looking at a signal on the spectrum analyzer coming out of the function generator, you can't really make the waveform stand still so it's centered on 0 and either is even or odd. It is what it is, and the instrument actually is not aware of the actual time origin. But what the instrument in the lab is aware of is whether or not the waveform has odd half-wave symmetry. And odd half-wave symmetry just means whether or not the waveform over one period is, over half a period, is flipped over amplitude-wise in the second half period. And a lot of waveforms we deal with have odd half-wave symmetry. A square wave is a prime example of that, and that's used as a clock signal in digital logic as well. There's a proof of that in here. I'm not going to go through it, but you can look at it. Trigonometric form, I'm not going to look at it either. It just follows from the complex sinusoid case from Euler's identity. It really just drops out from this property right here. And then this form, this one used to get taught in circuits when I was in school, and I bet you've never seen this one before. You did? In the circuits book?
Circuits 2 class.
Okay.
2
Okay. Well, we don't use it in this class, so don't worry about it. The complex sinusoid one is the best, and then this is the second best. And this one just falls out, like I said, from Euler's identity, pretty much. You're just basically folding things over from the positive and negative frequency axis, where you have either the plus j omega naught and either the minus j omega naught, and then looking at their coefficients and folding them to create a real cosine at an angle. And then this term stands alone because there's nothing to pair up the term at DC with. It just stands there all by itself. And what does x0 actually do in the waveform? So it just takes the waveform and just talks about whether or not you're raising or lowering it. Again, a coupling capacitor on a waveform will make that one go away. And in the lab with the spectrum analyzer, that's exactly what it has. It has a coupling capacitor on the input, so you do not see a spike at DC. If you see a spike at DC on a spectrum analyzer, it's added artificially. Sometimes in a spectrum analyzer they will add some reference line or something, but it's not part of the waveform. It's DC, it's AC coupled. And usually in a microwave or RF instrument, they don't want any DC getting in because it might destroy something. You know, you might accidentally have a line that has a bias voltage on it, and if it enters the instrument, it might blow something up. Okay, Parseval's theorem has to do with relating the total or the average power, which was what we were looking at earlier, with the sum of the magnitude squared of the Fourier coefficients. It just says that they're equal to each other. It's a handy result, and it actually relates back to that inner product idea I was talking about earlier. You decompose the signal into complex sinusoids, and you get the individual powers of the complex sinusoids, and that is equal to the total average power. It's like conservation of signal power when you decompose it like this. The total power is going to be there one place or another. It's distributed across the harmonics, or you can look at it as just the power in the waveform. So this is like the time domain view of it. And this is the spectral domain or frequency domain. And it can be useful if you're doing a certain type of calculation, because you can say what's the power in the first couple of harmonics divided by the power in the total signal to find out, you know, what fraction of the total power is contained in, say, the first couple of harmonics. To get the total power, it's easiest to work from this side over here. And if you wanted to get the fraction, then you would just use a few terms off of here. That makes sense, doesn't it? Just add up the power in the harmonics you're interested in, and you compare that to the total power. The line spectra, I think we've already talked about in the simplified form. This is just generalizing it for any Fourier series representation, saying that you've got the double-sided spectra just comes directly from the standard complex sinusoidal form. It can be simplified. You can interpret it for the single-sided spectra from this trig form if you want to, or just simply think of it as being involving twice the amplitude and just the positive angles. So it seems like I have a picture in here. So for the cosine squared example that we already looked at, I modified it by putting a phase in here, square it out. It looks like I have a typo in here. This must have been theta 1 originally, because I see a 2 theta 1 over here, and then 2 theta 1 up in there. So the two-sided spectra is going to have the DC component, and then it's going to have A over 4, which is what we had in that example, and A over 4 at minus 2f naught. So these are the second harmonics. The angle spectrum just plots the angle on the positive exponential as 2 theta 1 and then minus 2 theta 1 on the negative. And right there you can see symmetry too. Magnitude spectrum is even from the conjugate symmetry, and the phase spectrum is odd because the conjugate of a complex number has the angle that's the opposite in sign. The single-sided spectrum just collapses things down and only looks at the positive frequency, so the DC component stays the same, but this gets doubled because we're effectively taking this and bringing it onto that side to represent the amplitude, effective amplitude at the positive frequency. And that's what that trig form on the previous page was doing. And this is the spectrum analyzer. Model, except the spectrum analyzer won't be displaying the DC component, but it would display the A over 2, and then it displays it in power in dBm in a 50 ohm system. So there's a little bit more calculations in there. For those of you in the lab, though, I've got that in the lab sheet for doing that conversion to go from the amplitude and then the power in dBm in a 50 ohm system. You do that tomorrow probably, right? Is it? Okay, favorite time domain waveform is the pulse train. And this is a classic, actually. It's like the RC low-pass filter in circuits. This is a classic waveform to do a Fourier analysis of. It started in 2610. And this is a waveform that our new scopes from Agilent can generate too. Has anybody used the waveform capability on those scopes? Is it pretty nice? I think it's like incredibly nice. So you can adjust the duty cycle. Well, let me say for a second, what is the duty cycle? Do you on versus the time that it's off? So what's the duty cycle for this waveform as it's shown right here? Yeah, exactly. It's a number that ranges between 0 and 1, and you might give the duty cycle in percents, and then you'd multiply by 100. So this is a particular oriented pulse train, one that starts at 0, t equals 0, and turns on and then turns off at tau. But just like I was saying earlier, when you go in the lab and start playing with this pulse train, which you'll do in lab number 2, and we'll maybe model it in some other problems, it can be slid back and forth anywhere. And I have a theorem that comes up here shortly on that I'll get to before the end of the day, just to alleviate your concerns when you're in the lab about amplitude, because it doesn't alter the amplitude at all. The time alignment doesn't change the magnitude of the line spectra at all. But taking this exact form, a fancy way of writing out the pulse train would be with a sum that would take and have this doubly infinite superposition of rectangles. So when you see something like this, your eyes can bug out because I'm looking at my screen, you can look at the argument of the pulse and say, it's kind of heavily loaded with math. You look here and you say, what do I have inside of there? But then you can kind of calm down a bit and say, what happens if I just took that out of there? I would have a single rectangle centered at 0 of width tau. Okay, so now let's temporarily take that out of there. I have t minus tau over 2. So what's that going to do? That's just going to shift the pulse over to the right by tau over 2. And so the pulse was centered at 0, but now when I shift it over by tau over 2, it's centered at, well, when I shift it over by tau over 2, that's where it's centered at, tau over 2. Now, how do you remember things like that with functions? Well, what I always teach in 2610 is you go back to the core function. The core function is defined to be centered at 0, so it aligns itself at that location when the argument is 0. So you would just go back into the argument and say, when does t minus tau over 2 equal 0? You just solve that little equation there and say, oh, it's when t is equal to tau over 2, right? So if we now pull this off of here, and we add that in there for each value of n, we're just talking about a pulse that's shifted by a fixed offset of tau over 2, and then a variable offset to jump at multiples of t naught along the positive axis or along the negative axis. So n is equal to 0. This is the n is equal to 0 term. This is the n is equal to which? 1, right? Because a minus sign in there shifts it to the right. So this is n is equal to 1, and then what does this one have to be? Make it negative 1. And the dot, dot, dot just means going on for forever. When you go ahead and dive in to take the Fourier coefficient on this guy, the Fourier analysis equation just says, let me do one period. So you can pick any period you want to, right? That's what the beauty of the Fourier analysis equation, because it's periodic. My choice would be, to just pick this fundamental interval. I'd like to pick the interval so I only have one piece to integrate. It would be kind of dumb, but you could do it if you decided to integrate from here up to there. You could do that, right? But would a smart person do that? There might be a reason, but in this case I don't see a reason. Actually, for this problem, probably the easiest, another way of looking at it is saying I'll just integrate from minus t over 2 to plus t over 2, and then it's like it's right in the center of my vision, and it's 0 everywhere except from 0 to tau, so my limits on my integral are just 0 to tau. I still have to divide by t naught because that's part of the definition for the coefficient, to divide by the period, and then blast into it doing the integration of the complex exponential. Complex exponential is not any worse than a real exponential. You just have a j to carry around, so you don't freak out about that. You just have to remember the j is there when you do the integration. And then when you do the integration and plug in the limits, you get this. And that's acceptable, but it's not clean and pretty looking. So as tradition has it, when dealing with integrating a rectangle, you do some factoring. And the game that's played in signals and systems almost universally is to try to get things back into trig functions by manipulating using Euler's identity. So if you're, again, look on that same page in the appendix for the Euler's identity, you've got to be smart with those. But what you want to do here is say I have a 1 and some other complex exponential. Well, what you can do is factor something out of the 1 exponential in such a way that you're going to create a balance. And here the balance is the plus something and then the minus something that are of the same magnitude. So that way I know I'm building what? If I have a minus sign between them, I'm building a sine. If it was a plus, I'd be building up a cosine. So here I'm building up a sine. And I know when I build up a sine from Euler's identity, I have this 2j in there. So I make sure that sits in the denominator. If it's not already found there, what do I have to do? Yeah, exactly. So you can synthesize it into your math so that it'll turn into a sine, and then you might have an extra j hanging out in front somewhere. So I build that in, and that's where I get the sine. And then the leftover stuff is the pi n f naught tau. And then I've just got this linear phase factor, as it's called, hanging outside. And that is just present in there because we shifted the pulse by by tau over 2, actually. This actually comes from, if we put a 2 pi in here times n f naught, there would be a tau over 2 sitting in there. Remember, the initial pulse was shifted from being centered here, it was shifted over by tau over 2. That's the remnant from that, actually. Doesn't affect the magnitude of the Fourier coefficient because its magnitude of a complex exponential is 1. The further simplification is to call this term right here a sinc function, sine pi x over pi x. That's the Z&T, Ziemer and Tranter version. In some math programs, you will see sinc as sine x over x. So just be aware that it's different from different software tool makers. MATLAB, though, uses the correct, calling it the correct one, the one that our book uses. I'm trying to remember, I think Mathematica does not. Does anybody remember? I think Mathematica uses sine x over x.
So which one should we be using?
The one that's in our book. That's the correct one. I'm prejudiced like that. I'm saying our book is right. I'm just joking, but it's by far the more common way. But just be wary. I mean, your calculator might even have it. I don't remember. Does it? The TI-89?
No.
Okay. So let's see. I got to use the last 5 minutes very wisely now. I've got some pictures of line spectra in here that I just plotted using a function in MATLAB, and this is actually a function that I introduced in 2610. This is the listing of the function. It might be on the website too. I don't want to kill my remaining time, but let me just go take a quick look. If you're sitting in this tab here on the website and you hit this link called, well, actually that link or this link I think go to the same place. Let's just go to this one. I think it's the same thing now. If I'm working, yeah. It takes you into a directory listing of what's sitting down in there. And there it is right there. So there's some other little pieces floating around in here. That allocation chart that I showed you the other day. Remember the Federal Communications Commission? That's sitting in there too. Some other things we'll use later in the semester are hanging out in here. Projects from a year ago are hanging out in here. Code packages are hanging out. Phase lock loop, which we'll use in chapter 3, I've got some MATLAB models for that. So just be aware that's available. And if you're looking at stuff and you're wondering, is it new or old, the dates are over here. So if it's a project or something like that, it's not a valid project until it's got the correct date on it. I may change it. I don't know what I'll do, but I just haven't cleaned up my garage yet. It's kind of full of last year's litter, basically. Okay, so what we want to talk about is, we'll just look at the very first homework problem, since I wanted to spend a little bit of time on that, and then see what the first couple are. I've got the solutions that I posted. Everybody got the password, right, when I mailed it to you? Did it work, or has it worked for you? Okay. That'll be used for all kinds of things as time rolls on. Let's see, I didn't put the solutions, open them up in here today. What we're heading for is what we're going to have a quiz on. We're going to talk about that right now. So this problem right here is definitely a candidate because we already have talked about it some. This is basically a variation on the pulse train. Rather than having a rectangle in there, I've got a triangle in there. But it's a similar type of idea. And one of the calculations that was thrown in down here was to calculate the energy, or to calculate the power, I mean the average power. And then another calculation that could be done, and is not done in this problem, could be Fourier coefficients, which would involve the Fourier coefficients for a triangle. I'm probably not inclined to want to give that because that requires integration by parts, and I don't want to have you have to do that. We're actually going to have a much slicker way of doing that when we get to the Fourier transform. So I'm going to wait till I get more Fourier transform stuff done. But the contents of this problem is, in my opinion, totally viable for quiz material. This problem is a variation on the pulse train, looking at the coefficients formula. These are actually complementary waveforms, aren't they? If you look at them, one's the complement of the other. Or a property that I have for Fourier coefficients is related to adding constants and phase shifting. You could actually just invert the top waveform, in other words, flip it down like that, and then add a constant to it to raise it up, and you would have the waveform. Can you see how that would work? Adding a constant to a waveform, level shifting like that, doesn't do anything except change the x0 coefficient. Flipping the sign would change the angle by 180 degrees and everything, and that's kind of talked about in, I'm probably not, I'm not going to get into a question on that, but before class somebody said, are we going to have to draw sinc function spectra like I had Mathematica do? No, but I did say that a viable question for me is to say I could give you the sinc function spectra, and I could say, look at the sinc function spectra, and you can make some observations. One would be, if you were given a spectra like that, what are some things you can see right just from this amplitude spectrum? Yeah, there's a 0 right there at 4. So what does that tell you? The sinc function has its nulls at multiples of the pulse width, 1 over the pulse width. Now, except that 0 from L'Hopital's rule, it doesn't, it has 1 there. So that is 1 over tau, right? 1 over the pulse width. And this guy right in here, that location is 1. What's the spacing on the spectral lines in a Fourier series? The minimum spacing is what? Fundamental frequency. So that's the one that's right next to 0, so that must be the fundamental frequency. And so you could get F naught, and once you have F naught, then you have T naught, because they're the inverses of each other, right? So there, I can rig up something in a quiz. I think I have enough material to make a fairly simple quiz. So I would be familiar with these first two problems for sure. This is getting into Fourier transforms, which we didn't look at yet. So I will get something that you can spend 15 minutes on Thursday. Now, I guess I have to ask one quick question. My preference is to give the quiz at the end of the period. I know you fidget, but that way you can just get up and leave when you're done, and I'll force people to leave if they're not done by the end of the period. if I give it at the beginning, my thought is that you kind of are in this relaxed mode because you just did something, and then you're not as attentive, alert. But there's pros and cons to everything. Does anybody have a strong opinion now?
Are you going to put material that you taught during that class on the quizzes, or is that?
From today, you mean?
No, prior to it, if you did them at the end of class, would you put that material at the beginning of class on the quiz?
Oh, absolutely not. I'm writing the quiz based on what we just talked about. I talked myself through it, so I know what I have as my game plan, and so you know what I have as my game plan. And I'll probably put on. It'll take me a while to get the lecture video posted from today, but what I'll probably put on the website tonight when I'm processing the videos, I'll say the quiz is based on problems 1 and 2 from set number 1. And you'll be allowed to have your calculator, but a notebook computer is not necessary and anything like that. So.